Steel and fire will never take us to the stars, not because we are weak, not because we lack courage, but because the universe does not allow it. Interstellar travel is not hard. It is not expensive. It is not even far in the way we think about distance on Earth. It is physically impossible. That sounds dramatic. It sounds negative. It sounds like science fiction trying to kill hope. But this is not fiction. This is physics. And physics does not care about dreams. The universe has rules, and those rules are absolute. What if the greatest barrier between us and the stars is not technology, but reality itself? What if the speed of light is not just a number in a textbook, but a locked door that cannot be opened? In this video, you will learn why no engine, no matter how advanced, can push a spacecraft to light speed. You will learn why the closer we get to that cosmic limit, the heavier a ship becomes, until the energy required to move it rises toward infinity. You will learn why even a tiny grain of dust in deep space would strike a near light-speed ship with the force of a bomb. You will learn why time itself breaks apart when objects move extremely fast, turning interstellar missions into one-way journeys across centuries. And you will learn about lesser-known scientific realities that are rarely discussed in popular space documentaries, like the fact that the energy required to send a modest spacecraft to a nearby star at relativistic speed would rival the total energy output of entire nations over many years, or that proposed warp drives and wormholes demand forms of negative energy that may not exist in usable amounts anywhere in the cosmos. This is not about crushing hope. It is about understanding the limits written into the structure of space-time. Over a century ago, Albert Einstein showed through the theory of special relativity that the speed of light in vacuum is constant for all observers, no matter how fast they are moving. That single statement reshaped physics. It also sealed the fate of interstellar travel as we casually imagine it. As an object with mass moves faster, its relativistic energy increases dramatically. Each small increase in speed demands more energy than the last. As it approaches light speed, the required energy climbs without bound. Infinite energy would be needed to reach light speed. Infinite energy does not exist in a finite universe. This is not an engineering failure. It is a mathematical wall. Even the nearest star system, Proxima Centauri, sits about 4.24 light-years away from Earth. That number sounds small on a cosmic scale. It is not small for us. Light itself, the fastest thing in existence, takes more than 4 years to get there. Our fastest spacecraft, such as Voyager 1, would need tens of thousands of years to cover that distance. Civilizations rise and fall in less time. Languages are born and die in less time. Empires turn to dust in less time. Even if a spacecraft could travel at a significant fraction of light speed, another problem appears: time dilation. According to relativity, time slows down for objects moving very fast relative to an observer. For astronauts on a near light speed journey, a trip to a distant star might feel shorter, but for people on Earth, decades or centuries would pass. They would return to a planet that no longer recognizes them. Interstellar travel does not just stretch space, it fractures time. Then there is the hidden danger of interstellar space itself. It is not empty. It contains sparse atoms, charged particles, and microscopic dust. At everyday speeds, these particles are harmless. At speeds close to light, they become deadly. A tiny speck of dust, impacting a spacecraft at relativistic velocity, would release enormous kinetic energy. Shielding against such impacts would require massive protection. More mass means more energy required for acceleration. More energy means more fuel. More fuel means more mass. The problem loops back on itself. Some argue that advanced propulsion systems, antimatter engines, or fusion drives could solve these issues. Fusion remains difficult, even inside controlled reactors on Earth. Antimatter is incredibly energy-dense, but producing even tiny amounts requires vast energy inputs, and storing it safely is another challenge entirely. The energy bookkeeping never works in our favor. Others place their hope in wormholes or warp drives. Theoretical models like the Alcubierre drive suggest that space-time itself could be warped, allowing a bubble of space to move faster than light without locally breaking relativity. But the equations demand exotic matter with negative energy density. While small quantum effects hint at negative energy in limited situations, no known mechanism provides it in the enormous quantities required. Some calculations suggest that the energy needed would rival the mass energy of entire planets or stars. These are not small technical details. They are fundamental barriers. Throughout this video, we will break down each of these constraints carefully and clearly. You will see how the universe enforces its speed limit, how energy requirements explode as velocity rises, how time itself becomes distorted, and how even empty space turns hostile at extreme speeds. By the end, you will understand that the phrase physically impossible is not dramatic exaggeration. It is a conclusion drawn from equations tested again and again for more than 100 years. Stay with this until the end, because the final insight is not about despair, it is about perspective. When we accept that the stars may be forever beyond our physical reach, we begin to see our place in the cosmos differently. The universe may allow observation, exploration through telescopes, and signals that cross light years, but it may forbid physical crossing. That changes how we think about our future. That changes how we think about survival, expansion, and destiny. This channel exists to explore truths like this. Not fantasy, not hype, but the real laws that govern reality. If you are curious about the deep structure of the universe, if you want to understand what is truly possible and what is forever locked away, then you are in the right place. Welcome to our channel. Subscribe now and stay with us as we uncover the physics that shapes our limits and defines our future among the stars. For thousands of years, the night sky has pulled at the human mind like a quiet magnet. Ancient civilizations looked up and mapped the stars with patience and wonder. Sailors used them to cross oceans. Farmers used them to measure seasons. Philosophers built myths around them. Today, the myths are gone, replaced by rockets and equations, but the desire remains the same. Humans want to reach other stars. The dream did not begin with modern science. It is older than recorded history. Now it wears a new face. We picture massive starships crossing deep space. We design sleek spacecraft in movies and simulations. We talk about colonies orbiting distant suns. We speak about new Earths waiting to be claimed. Some even talk about escape, a backup plan, if our planet becomes unlivable. The idea feels logical. The universe is vast. There are billions of stars in our galaxy alone. Surely we can travel to at least one of them. Surely distance is just a challenge of engineering. Yet the first reality check is quiet and brutal. The nearest star system to Earth is Proxima Centauri, part of the Alpha Centauri system. It is about 4.24 light years away, often rounded to about 4.3 or 4.37 light years in public discussions. That number sounds small when spoken quickly. 4-point-something light years. It hides its scale well. 1 light year is the distance light travels in 1 year, at about 300,000 kilometers per second. Multiply that by seconds in a year, and the result becomes overwhelming. Over 9 trillion kilometers in a single light year. Multiply again by more than 4, and the distance climbs above 40 trillion kilometers. That is just the nearest star. Our fastest spacecraft, Voyager 1, is traveling at roughly 17 kilometers per second relative to the Sun. At that speed, reaching Proxima Centauri would take tens of thousands of years. Some estimates place it above 70,000 years. Human civilization as we know it is only a few thousand years old. Written history is shorter than that journey would be. Even if we built a craft 10 times faster than Voyager, it would still take thousands of years. Generations would be born and die inside a single mission. But distance, as extreme as it is not the deepest problem. If it were only about distance, we could imagine steady improvement, faster engines, better fuels, larger ships. Distance is a number. Physics is a law. The real barrier begins with the ultimate speed limit of the universe. In 1905, Albert Einstein introduced special relativity. One of its central statements is simple and unforgiving. The speed of light in vacuum is the same for all observers, no matter how they move. It is not just the speed of light, it is the maximum speed at which information or influence can travel. Nothing with mass can reach that speed. As an object moves faster, its relativistic energy increases. The equations show that as velocity approaches the speed of light, the factor that links energy and motion grows without bound. In simple terms, the faster a massive object moves, the harder it becomes to make it move even faster. Each small increase in speed demands more energy than the last. At low speeds, the increase is manageable. At very high speeds, near the speed of light, the required energy grows dramatically. To actually reach light speed would require infinite energy. Infinite energy is not available in a universe with finite mass and finite stars. This is not a matter of better engines. It is not a matter of clever design. It is built into the structure of spacetime. Older explanations often said that mass increases with speed. Modern physics phrases it more carefully, saying that the total energy and momentum increase in a way that makes further acceleration harder and harder. The effect is the same in practice. As speed rises, the ship resists acceleration more strongly. Imagine pushing a car. At first it moves easily. Now imagine that with every push the car becomes heavier. Not a little heavier, dramatically heavier. That is what relativity does at extreme speeds. So even if we build the most advanced propulsion system possible under known physics, the ship will always remain below light speed. It may approach 90% of light speed, 99%, even 99.9%, but each additional fraction demands enormous extra energy. The curve rises steeply. The finish line retreats forever. Even the fastest possible ship will always be too slow for easy interstellar travel. Then comes the energy problem in practical terms. Consider a spacecraft with significant mass, not a tiny probe, a vessel capable of carrying humans, life support systems, radiation shielding, supplies, and perhaps equipment to build a colony. Such a craft could weigh thousands or millions of tons. To accelerate that mass to even a fraction of light speed would require staggering energy. The kinetic energy at relativistic speeds does not follow the simple half v² rule taught in early physics classes. It grows much faster as velocity approaches light speed. For a ship traveling at 90% of light speed, the energy required is several times the rest mass energy of the ship multiplied by relativistic factors. Even rough estimates show numbers that rival the annual energy consumption of entire nations. Some calculations suggest that sending a modest interstellar craft at high relativistic speed would require energy comparable to years of total global energy production. And that is only for acceleration. To slow down at the destination would require similar energy again. Fuel adds another layer of difficulty. In rocketry, fuel itself has mass. To accelerate fuel, you need more fuel. That additional fuel adds mass, which requires even more fuel to accelerate. This is known as the rocket equation problem. The required mass of fuel grows exponentially with the desired change in velocity. At relativistic speeds, this becomes extreme. If we imagine a conventional rocket carrying its own fuel, the amount of propellant required to reach near light speed becomes absurd. The ship would need to be mostly fuel. Then to accelerate that fuel, even more fuel would be required. The loop becomes a physical trap. Engineers can optimize, they can improve efficiency, they can use better materials, but they cannot escape the exponential nature of the rocket equation, combined with relativistic energy growth. This is not a temporary obstacle waiting for better technology. It is a consequence of mathematics rooted in spacetime itself. Even proposals using antimatter face limits. Antimatter annihilation converts mass directly into energy, with high efficiency, yet producing antimatter requires vast energy input in particle accelerators. Current production rates are tiny. Storing antimatter safely is extremely difficult because it annihilates on contact with normal matter. Even if production and storage problems were solved, the total energy demands for a large relativistic spacecraft remain immense. The numbers do not shrink into something comfortable, they stay astronomical. Then there is the hidden catch that changes how we think about the journey itself. Time dilation. According to special relativity, time does not flow at the same rate for all observers. For an object moving at high velocity relative to another, time slows down. If astronauts travel at near light speed, their clocks tick more slowly compared to clocks on Earth. From their perspective, the trip might take only a few years. From Earth's perspective, decades or centuries may pass. This creates a strange disconnect. The travelers might reach another star within their lifetime, but when or if they return, everyone they knew could be gone. Entire cultures could have changed. Languages could have shifted. Political systems could have transformed beyond recognition. Even if a mission succeeds physically, it fractures continuity with Earth. It turns interstellar travel into a one-way journey across time as well as space. A colony established around another star would not simply be far away, it would be separated by years of communication delay, and by deep time differences created by relativistic motion. Messages traveling at light speed would still take years to cross the gap. There would be no real-time conversation, no quick rescue, no shared daily life. Interstellar travel disconnects time itself. The dream of spreading humanity across the galaxy begins to look less like expansion and more like permanent isolation. As if distance and energy were not enough, space itself presents another problem. Deep space is often described as empty. It is not empty. It contains sparse hydrogen atoms, cosmic rays, and tiny grains of dust. The density is low compared to Earth's atmosphere, but over light-year distances, encounters become inevitable. At normal spacecraft speeds, these particles cause minimal damage.
At relativistic speeds, the situation changes completely. The kinetic energy of an object increases with the square of velocity in classical physics, and even more dramatically under relativistic conditions. A microscopic dust grain hitting a ship traveling at a significant fraction of light speed would release enormous energy. The impact could puncture shielding, damage critical systems, or create secondary radiation. To protect against this, a spacecraft would require heavy shielding at the front. That shielding adds mass. Added mass increases energy requirements. Increased energy requirements demand more fuel or larger power systems. Those systems add mass again. The cycle repeats. Even interstellar hydrogen atoms, which are normally harmless, become a source of radiation at extreme speeds. As the ship plows through space, these atoms would strike the hull with high energy, creating showers of secondary particles. The front of the ship would face a constant stream of high-energy impacts. Shielding against this would not be optional. It would be essential for survival, and shielding is heavy. Each solution deepens the mass and energy problem, rather than solving it cleanly. Faced with these limits, many people turn to more exotic ideas. Wormholes are a popular concept. In theory, general relativity allows solutions where space-time is curved in such a way that two distant regions are connected by a tunnel. If such a wormhole existed and were stable, one could enter at one mouth, and exit near a distant star almost instantly from an outside perspective. The mathematics is intriguing. The obstacle lies in stability. Known solutions suggest that to keep a wormhole open and prevent it from collapsing, exotic matter with negative energy density would be required. Negative energy density is not ordinary matter. Certain quantum effects such as the Casimir effect show that small regions of space can exhibit negative energy relative to a reference state, but these effects are tiny and occur under very specific conditions. There is no known method to accumulate or control negative energy in the massive quantities required to stabilize a macroscopic wormhole. Without that exotic matter, the wormhole would pinch off too quickly for travel. Warp drives present a similar story. The Alcubierre metric is a solution to Einstein's field equations, in which a bubble of spacetime contracts in front of a ship and expands behind it, effectively allowing faster than light travel without locally breaking the speed limit. Inside the bubble, the ship remains stationary relative to its local spacetime. The bubble itself moves. It is a clever mathematical idea, yet it also demands negative energy densities and enormous total energy. Early estimates suggested energy comparable to the mass energy of entire stars. Later refinements reduced the requirement, but it remains extreme and depends on forms of matter we do not know how to create or sustain. Even if negative energy could be produced in small amounts, shaping it into a stable warp bubble introduces further complications. The mathematics does not easily translate into engineering. Every time we push deeper into these speculative solutions, we encounter the same barrier. The universe does not yield easily. At every scale, from energy to time to space-time geometry, limits appear. This leads to a deeper question about our expectations. Perhaps the universe is not structured for physical crossing on interstellar scales. Perhaps visibility does not imply accessibility. We can see galaxies billions of light years away. We can detect exoplanets orbiting distant stars. We can measure the chemical composition of atmospheres from faint spectral lines. Observation travels at light speed and requires no mass transport. Knowledge spreads freely across space. Matter does not. Maybe stars are visible but unreachable in any practical sense for biological beings like us. We evolved on a planet with moderate gravity, a protective atmosphere, and abundant resources. The laws that govern atomic structure and energy also govern propulsion and motion. Those laws permit flight within atmospheres. They permit travel between nearby planets with great effort. They may not permit easy crossing between stars. The dream of interstellar expansion might be shaped more by imagination than by physical possibility. Curiosity is allowed, conquest may not be. The universe reveals itself through light, through gravitational waves, through neutrinos. It shares information generously. Yet it sets strict limits on the transport of mass, and on the speed at which cause can influence effect. In that sense, the cosmos invites us to look, to measure, to understand. It does not promise that we can go everywhere we can see. The boundary between observation and possession may be permanent. As we continue exploring physics, each layer of understanding sharpens that boundary, rather than erasing it.
Interstellar travel is not impossible because we are weak. It is not impossible because we lack intelligence, courage, or ambition. Humanity has split the atom. We have walked on the moon. We have sent machines beyond the edge of the solar system. This is not about failure. It is about rules. The universe is not built on wishes. It is built on laws, and those laws do not bend for dreams. The speed of light stands like a wall. Energy demands rise beyond reason. Time stretches and separates worlds. Space itself turns hostile at extreme speeds. Every path we examine leads back to the same conclusion. Not yet, not later, but never, under the physics we understand. Interstellar travel is not impossible because we are weak. It is impossible because reality has rules. That truth may feel heavy at first. For generations, stories have promised that one day we will spread across the galaxy. Science fiction shows starships moving freely between distant suns. The idea feels natural. If we can cross oceans, we can cross space. If we can fly across continents, we can fly to other stars. But oceans do not resist us with infinite energy barriers. Continents do not slow our clocks and tear time apart. The leap from planet to planet is enormous. The leap from star to star is something else entirely. It is not just a bigger step, it is a different category of challenge, a challenge written into space-time itself. The stars are not far away in a simple sense. They shine in our sky every night. Their light reaches us without effort. Some of that light began its journey before human civilization even existed. The photons cross the darkness easily. They are massless. They obey the rules perfectly. We, on the other hand, carry mass. We carry weight, and weight ties us to the limits of the universe. The stars are not far away. They are separated from us by the laws of existence. And maybe that changes the way we see our place in the cosmos. Maybe the future of humanity is not about spreading endlessly outward. Maybe it is about going deeper instead of farther, deeper into understanding, deeper into physics, deeper into the structure of reality itself. The same laws that stop us from reaching other stars also allow atoms to exist. They allow chemistry. They allow life. The limits are not cruel. They are consistent. They create the very stability that lets us ask these questions. When we accept limits, we do not shrink. We become clearer. We stop chasing illusions and start exploring what is truly possible. We refine propulsion for the solar system. We build better telescopes. We search for life through signals instead of ships. We turn our curiosity into knowledge instead of conquest. The universe may not be a place we can physically dominate. It may be a place we are meant to understand. If this changed how you see the universe, then stay with us. This channel is about facing reality without fear. It is about exploring the deepest truths of physics, even when they challenge our favorite dreams. Because the deeper we look into physics, the more limits we discover. And inside those limits, we find something even more powerful than fantasy. We find truth. Subscribe now so you do not miss what comes next. Like this video. If it made you think differently, share it with someone who still believes the stars are just waiting for us to visit. And join us as we continue to explore the laws that shape existence itself.